So, hi everyone, this is Miss Folly, and this is chapter 11 entitled as a direct current. This chapter will be divided into two parts, part A and part B. And as I said earlier, the whole parts or all the whole chapters will be in online classrooms. So please watch all the video provided and also do your exercise. So before we start, I would like to bring your attention to the story of the direct current and alternating currents. So I hope you already watched the movie that I recommended to you about a story about the war between the founder of direct current and also alternating current. So this is Thomas Edison. He is the founder of the direct current, and this is Nikola Tesla, a French physicist, which is the founder of alternating current. I think it is better if we understand what is the difference between DC and AC. So DC is basically the flow of electricity in one directions only. And the system of DC is operate at the same voltage level throughout and is not efficient for high voltage. So but then DC is a long distance transmissions and is the direct current will run through. Now, for AC, which is alternating current, it is an electric charge periodically reverse direction and is transmitted to customer by a transformer that could handle much higher voltage. So AC is basically can be run through um, car motors, radio signals, and appliances. So this is the story of Thomas Edison and Nikola Tesla. Okay, this is the outline of both part for this chapter. The first part we will focus on electric current, resistance, resistivity, and Ohm's law. Previous chapter you did learn about capacitor, which is the name of the instrument, capacitance, which is the measurements that use capacitor in your what is it in your circuit, and farad as um, the unit of the capacitance itself. Now in this chapter we will focus on resistor and resistance, also resistivity, and the relations of this resistance to Ohm's law. And then we will see on the electric energy and power. And last but not least, in this part, we will see a little bit, understanding a little bit on superconductors. Now, on part 2 will be a little bit hard. So, on part 2 of this chapter, we will focus on understanding what is EMF. EMF is electromotive forces. And then after that, we will see a difference between a series and parallel of resistors. So how to find the voltage total, how to find the current total, or what is the effect to the resistance itself. We will see it in this part. Last but not least, which is the key point of this part, is the Kirchhoff law itself. So Kirchhoff law is one of the process or procedure on how to find current, voltage, or resistance for complex circuit. Now I need you to pay attention to the third part of this part because this will be your highest mark in your final exam. So first and foremost, what is electric current? So the current or the electric current is defined as the rate at which charge flow through a surface. So when we talk about the rate, it's supposed to be divided by the total of the time or the differences of time. So suppose delta Q is the amount of the charge flow through one area, which we symbolize as A, in a time interval, which is delta T. So the average current, or we symbolize is I, AV is stand for average, is equal to delta Q divided by delta T. So since Q, the symbol, the SI unit for Q is coulomb, and SI unit for time is second, so SI unit for this current average is equal to coulomb per second, or also known as ampere, right? The second term for electric current is instantaneous current. So instantaneous current is a number or amount of charge or amount of a very small charge flow through an area. So the equations is basically same with the average current, but then as it is a very small number of current that pass through in one area, so it has limitations to zero. So this is electric current in definitions. Another terms that very important for electric current is drift velocity. So what is drift velocity? Let's say since electric current is quantized in discrete multiples of the electron charges, it is instructive to look at electric current as the movement of multiple microscopic charge carrier with a drift velocity. So drift velocity is similar with the velocity that you already know. But then this drift velocity here is stand for the velocity that um, uh, that owned by this charge carrier. Now, so how to find this drift velocity? Drift velocity is equal to or symbolized as the Vd here. So this is drift velocity. So for let's say n is the number of charges of electron per unit volume. So I know that Q, which is the charge, is equal to the total, oh no, the times of the number of charges electron times with the number of electron itself with times with the area and times with the distance. So for let's say I have a container, a cylinder container here. So the electron is moving from this part to this part or from this part to this part with a distance of d, and this cylinder has an area, surface area of A. So let's say this is my current measuring point. So the movement of this electron from this point to this point is what we call as a drift velocity. So the total charge for all of this particular electron here in this part is equal to n times with the E times with the A, the area, times with the distance. So this is the total mobile charge in length of this conductor. So we know that from velocity, velocity is also equal to the distance divided by time. So when we rearrange that equation, we will get these equations, which is time for this charge to sweep past the current measuring point. Now, by substituting this T into this Q over here, you will get a new equation, which is stand for your current. So I know that current is equal to charge divided by T from previous definitions. So by substituting Q is equal to this one and T equal to this one into this equation, you will get an equations with the drift velocity in it is equal to this one. So current is also equal to the number of charge times with the number of electron times with the A, which is our area, times with the drift velocity. So if I need to find the drift velocity, if I was given I and E and A, just rearrange this equation, I will get the value of drift velocity. So that was drift velocity. Once again, what is drift velocity? Drift velocity is the average velocity that was owned by this charge carrier to pass this current measuring point. So that was drift velocity. Right. So we're moving on to the resistance and Ohm's law. So what is resistance? Resistance is electrical resistance is the hindrance to the flow of charge through an electric circuit. Okay. Now Resistance also ratio of the voltage across the conductor to the current it carries. And resistance is with Ohm's law, resistance is equal to the delta V divided by the current. And the SI unit of the resistance, as you all know, is equal to ohms. And the symbol is this one. So that was resistance. Now, what is the relations of resistance and Ohm's law? It is stated in by the Ohm's law itself. So R is for the resistance, V is for the voltage, which is the SI unit is volt, I is the current, which is the SI unit for current is ampere. There are two types of conductor that you need to know. First, we call it as a ohmic conductor, which is conductor that obey Ohm's law. So what is the example of this ohmic conductor is pure metals. So what is the meaning of conductor that obey Ohm's law? It is that can show in a graph. So let's say I have a graph of V versus I here. As you can see here, as the value of current is increasing, the value of V is also increasing. This is due to Ohm's law, because Ohm's law states that V over I is equal to R. So the number of the gradient here for this particular graph is also equal to the value of the resistance for this pure metal. Now what is the non-ohmic conductor? Non-ohmic conductor is any conductor that do not obey Ohm's law. For example, a junction diode. A junction diode can pass through any current, but then it does not obey Ohm's law. So what is the meaning of not obey Ohm's law? It's that when the value of V is increasing, the value of I is decreasing. So it is supposed to be different with the Ohm's law itself. The next term that you need to know is resistivity. So resistivity is some kind of it's siblings to resistance, but it's not similar to resistance. So resistivity is a measure of the resistance of a given size of a specific material to electrical conduction. So for example, resistance is for the resistor, but resistivity is actually for any basic instruments of the circuit. For example, I have a lamp, or I have a capacitance, or I have an inductor, or I have a power supply. So each of that basic instrument will have their own resistivity, own resistance, which we call it as a resistivity. Now, resistivity in this particular slide was referred to the resistivity owned by the resistor itself. So resistivity be referred to as the specific electrical resistance or volume resistivity, although these terms are less widely used. So resistivity was symbolized as this symbol, our rho, and the relation between resistivity and the resistance is equal to R equal to the density, the resistivity times with the length divided by the area. So that was resistivity, right? So this is the means of each for this term. Okay, so this table, you can find this table in your books or any or you can Google it easily. You don't have to memorize this one because every materials or different material will have their own resistivity. So I will not expect you to memorize it, but I just need you to know that different material will have a different resistivity. Hence, they also have different coefficients of resistivity. So, for example, our silver here has this value of resistivity. Copper has a value of this, and so on. So that was resistivity. Right. So I have two examples here. First example is ask you to find or calculate the resistance per unit length of a 22 gauge nichrome wire with the radius of 0.3 to 1 millimeter. And B, if a potential difference of 10 volt is maintained across the 1 meter length of the nichrome wire, what is the current in the wire? So the first question was asked you to find the resistance per unit length, and the second questions was asked you to find the current. So this is the solutions of it. Our you can start with the area, which area for wire is pi r square. So substitute the r that was given to you, you will get an area here. Now by using the equations of R is equal to resistivity times width the length divided by area, rearrange it because you need to find resistance over length, so you will get this value as the answer. The second question asks you to find the current, so you can use directly the Ohm's law and you will get 2.2 ampere as the value of current. This is quite easy examples. Right. Now this is the next term which is quite similar with resistivity, conductivity. So what is conductivity? Conductivity is the material ability to conduct electricity. That was conductivity because it is similar with conductor. Electric current can flow easily through a material with high conductivity, so obviously because it is the ability to conduct electricity. And conductivity is measured in Siemens per meter, or it also can be written as this one. So it's a Greek letter for Siemens per meter. We use this symbol to represent our conductivity, which is the Greek letter. And the relations of conductivity of material with the resistivity is actually a reciprocal. So conductivity is equal to 1 over resistivity, and since resistivity is equal to R divided by L times with the area, from R is equal to resistivity times with the length divided by the area. By rearranging this one, I will get the value of resistivity, and rearrange this one, I will get new relations between my length, area, and resistance with my conductivity. So this is conductivity and resistivity. Right. Another thing that you need to know about resistivity, that it can be affected by temperatures. So temperature is the only factor that can affect the value of your resistivity. So for, let's say this is the value of R here. This is the relations of resistance and resistivity. And the relations of resistivity with the temperature is equal to this one. So resistivity equal to the initial resistivity. This initial resistivity is actually when T, temperature, is equal to 20 degrees Celsius. Okay. Usually the initial resistivity will start from the temperature is equal to 20 degrees Celsius. So for example, the resistivity of gold will be different at 20 degrees Celsius and at 80 degrees Celsius. So what is the initials? Initial is at the at the temperature is equal to 20 degrees Celsius. Times with the 1 plus with the alpha here, which is alpha is equal to the coefficients of resistivity. You did see this value in my table just now, and I need to remind you that you don't have to memorize all of it, because I will provided it to you during your exam. Times with the t equal minus with the t naught, which is this t naught will be usually on 20 degrees Celsius if it is not stated in your questions. But then if it is stated in your questions, then just follow the questions then. Okay, so this is the relations between my resistivity and the temperature. Right. So when I substitute this one into this one, I also have a new relations between my resistance and also temperature, which is basically same with this resistivity. I just change the value of resistivity with the resistance, so it's actually similar. So as you can see here from this relationship, when the delta T is higher, then the R over here will be higher if this is constant. So that was the relations between the resistivity, the resistance, and temperature. Right, so from that equation that we see just now, that we described just now, it is conclude that the resistance of a metal is actually depends on these three parts. The first one is the nature of the material, which in this case the nature of material is the resistivity itself. So when the resistivity of the metal or the conductor is higher, then the value of current that can pass through to that conductor is also lower due to V is equal to IR, right? The second element that can be affect our resistance of the metal is the size of the conductor, which is in this case size is stand for the length and the cross-sectional area. Last but not least is of course the temperature of the conductor. So the higher the temperature, the higher the resistance. When the resistance is higher, then the value of I is lower. Right? So you can read these 3 points that I provide to you. This is actually more on explanations to these 3 basic points. So you can read more on this, or you can also find your own source on the description or the explanations of these 3. So I have an example here. We have electrical resistance with temperature. We have a platinum here, and this platinum at the initial temperature is 20 degrees Celsius. It has a resistance with the value of 164.2 ohm, and you were asked to find the final temperature when the resistance is equal to this one. So I have my initial temperature, initial resistance, final resistance, and last but not least, I was asked to find the temperature of the solutions. So just using these equations, as I said earlier, this is a various number for material, so don't memorize it. I will give to you, I will provide it to you during your exam. So in these particular equations, platinum has a value of coefficients of capacitance is equal to 3.927 to the power of -3. So by substituting everything, before that, by rearranging everything, because I need to find the final temperature, by rearranging it, I will get this equation, the new equation from this one. Substituting everything, remember I will use the degree Celsius here. I'm not going to change it into Kelvin unless I have to give the answer in Kelvin or any other SI units. So other than that, I will stick with the degree Celsius. So substitute everything, you will get your final answer is equal to 56 degrees Celsius. So this is the final temperature when the resistance is equal to this value. Now, we move on to the next subtopic, which is electrical energy and power. Before that, what is the difference between this electrical energy and this electrical power? It's it's pretty similar, but it's actually a very different things. So electrical energy is the work done. Remember, this is a work done. It's a work done or energy supply by the source in maintaining the flow of electrical current. We call it as a electrical energy. It appears in the form of heat. See, it appears in the form of heat. And it is given by this equation, which is heat. This is Q. You usually know this as a Q, but then in this particular slide, I will, no, I'm using H as the symbol of heat, is equal to the product of voltage, current, and time. So by substituting this V I equal to from Ohm's law, I will get a new equations for it. Rearrange it, I will get this value of Q. So it is also, the work done is also equal to the product of power and time. So work done is equal, work energy is equal to P times with the T. And the SI unit for energy is equal to joule, obviously, because it is energy. The second one is electric power. Now, as you realize that the definitions of electrical power is start with the time rate. So we have read here which is involves time. So electrical power is the time rate at which electric energy is consumed or dissipated by an electrical device is called an electrical power. So electrical power is obviously equal to this equation. P is equal to VI, where P is the power, V is the voltage, I is the current. By substituting our Ohm's law here, I will get a new form of relation between VR and P, which is equal to this one. Substituting again the value of Ohm's law, I will get this one which related to P. So once again, I need to emphasize the difference of electrical energy and electrical power. Electrical energy is work done or energy supply. But then electrical power is the time rate, which is electric energy is consumed or lost or dissipated. So it's a quite difference between these two. Power also can be written as this one. P is equal to W over T, which is W is the work over T, T is time. And the SI unit of electrical power is watt, W. You need to know that 1 watt is also equal to 1 over joule per second. So, alright, so this is basically similar with this one. This is more on conclusions between electrical energy and power, but then this is specifically to the equation itself. So electrical energy is equal to this one. This is the equations. I know that Q is the heat, is the charge, and charge is equal to current times with the time. So we will get our energy here. The SI unit is joule because it is energy, and power is equal to this one. P is equal to W over T. We know that work is energy is also equal to 3 Q over QV from this one. So I will get a new equation here. The SI unit for power is equal to watt, which is equal to 1 over joule per second. Right. So yes, this is a power, an equation for power for any device. But then as for resistor, I will use this two equations, either this one or this one. This is due to the existence of resistance, so I have to consider resistance into my equations. As you can see, the original equation, which is this one, which available for any devices, there is no symbol for resistance over here. So if I need to find a power that was used or dissipated in a circuit with the existence of resistor in that circuit, I have to use these equations. It is basically replacing the Ohm's law, V is equal to IR, into this equation, and you will get a new equations for resistors. So I have an example here. I have an electrical heater which operated by applying a potential difference 50V to a nichrome wire with the total resistance of nichrome wire is 8 ohm. So my first question was asked to find the current, so I need to find I. The second question, by using this heater with the number of mole is equal to this one, and this is a diatomic gas. So I was given the initial temperature and the final temperature. I need to find how long it is to heat. So I need to find T, which this one I was given an extra information. The molar specific heat at constant value of A is to be 5/2 times beta R. So this is the solution for the first part. Since I need to find current, so this is the solutions. And then on the second equations, I was asked to find the T. So I will start from my Q charge here, where Q is equal to N, which is number of mole, times with the CV times with the delta T. I have all of these. This is molar specific heat. So substitute everything, I will get my value of Q. And from P is equal to Q times with the T. So I will get this answer as the time taken to heat. Right? So that was the equations and the solutions. Now, this is my last, I think this is my last subtopic for this part, which is superconductor. I just need you to understand what is actually superconductor. So superconductor is a material that can conduct electricity, yes, of course, because it is superconductors, or transport electron from one atom to another. This is special with no resistance. Now, for example, I'm using a copper wire to transfer an electrons from point A to point B. I will observe that the power from point A to point B will be different due to the resistance that owned by the copper itself. But for superconductor, any material that has the characteristics of superconductor, when the electrons was moved from one point to another point using a superconductor, you will observe that P in this point, power of this point, and P at this point will be similar. So if you send 100% of power here, you will get 100% of power here. This is due to this type of material has no resistance at all. So there is no loss in power, no hindrance in the movement of electron itself. So that was superconductor. And what is most special of superconductor is there is no heat. Sound or any other form of energy will be released. So that's why what you transfer from here, you will get it 100% in here, because there will be no heat that lost during this movement of electron, there is no sound, and also there is no other energy that was released. Now, when this will happen, this is only happen when the critical temperature, or also symbolized as Tc, is uh, in conditions. Okay. Now, for let's say these materials are in critical temperature, and you are passing through an electron here from this point to this point, you will observe that there is no heat, sound, or other form energy will be released, so the work done will be 100% done, right? Most material must be in an extremely low energy state. This is um, one of the hindrance in superconductor, because it must be extremely low energy state in order to become a superconductor. So it is hard to produce a superconductor actually. Now currently an excessive amount of energy must be used in the cooling process, making superconductor inefficient and uneconomical. So as I said earlier, superconductor is only exists when this is happen, electrical temperature, critical temperature happen, which is the lowest temperature at all. Now, to reach this particular critical temperature, there is an excessive amount we need to use to produce a cooling process. So that's why a superconductor in particular is actually quite hard to produce. So that was superconductor. Now, this is a few element in your periodic table that has a characteristic of superconductor. So the blue one is at ambient pressure, while the green one is only under high pressure. When, let's say, silicon over here put in a container with under high pressure, it will produce a superconductor. That was the difference. So for let's say I have a plumb bomb here, when I have ambient pressure, which is a very normal pressure, it also can reach a superconductor level. So that's all for the first part. I will continue the second part in the next video. Thank you.